Do you have the problems with you?
What about
14? Okay. Well, 8, I did not give you the information that you needed to do that, so I'm sorry about that. Okay, well, here's the deal with the relationship. So my plan was to skip those, but this is useful. Just not as useful as some of the other stuff. Okay, so the relationship between the potential energy function and the force field. That's what we're looking for. This is 8, as it says right there. 8, number 8. And this relationship is that the x component of the force is equal to the negative. Okay, I'm going to do something that looks familiar but new to most of you. Du dx. That's a partial derivative. How many of you have had partial derivatives before? Okay, so it's an easy idea, but so I'll explain it to you. One thing that's cool about it is that whenever you see geniuses in movies, the way they indicate that it's a genius is they're doing partial derivatives on a window in a marker. And now you'll know, like if you do this on a window with markers. Yeah, exactly. I don't know. That's just they always do it. I'm not really a movie maker, so I don't know. What? Yeah. And actually, so it would have been way beyond expectations for you to figure this out, but it would have been possible to figure kind of out this relationship if you thought of potential energy, the change in potential energy, as the negative work. And then you know the integral relationship between force and work. But that, I didn't expect you to do that. I just wasn't really planning to sign these problems, and I did. Okay, so a partial derivative, the way you do a partial derivative is you assume all other variables are constant. And that's all there is to it. So, like partial derivative with respect to x of 5x squared y squared z is just, you assume that the y squared z is a constant, and so you have 10x y squared z. So you just treat those other variables like they're numbers, you know. Why do you do that? What's the point of it? Well, what you're doing is, you know, oh, well, you haven't done directional derivatives either. Well, you could imagine, okay, so say you got this three-dimensional thing. Those contour lines are supposed to indicate that this is three-dimensional. Maybe you have something going on in here too, you know, a little valley in there. Okay. Well, in 2D, in a function, you know, y is a function of x. Talking about the slope is that's a well-defined question. You know, it only has one slope. But if you're talking at this point, what's the slope there? You can imagine, imagine this being a hill that you're walking on, and someone's like, what's the slope up there? And you're like, well, I don't know, which direction are you walking, you know? Because it's flat if you go this way, but it's steep if you go this way. You know what I mean? And so that's the idea of partial derivatives. You're saying, well, if the coordinate system is like this, the partial derivative with respect to x is the slope of this hill if you're moving, you know, to the right of the page. With respect to y is if you're moving. What? Yeah, that's right. So it's just telling you the difference. I almost said steps. It's steepness. That would let you sort of. So, and you can use it in a bunch of ways, you know. So, because obviously there's more than just three directions you can walk on the hill. There's infinitely many, but you can use this idea to get at those slopes in all the different directions. Okay, so think of the hill and trying to tell someone how steep the hill is. That's what the partial derivatives are. Yes. Okay. Well, so now it's pretty simple to find this. If this potential energy function is 4 times the quantity 2 minus x all squared, then fx is equal to d dx of this. Okay. Well, it's only a function of x, so this is just the same as the derivative. You know, just like if you're on a hill and you can only go one direction, then does it give a? So it's 8 times 2 minus x to the first times negative 1. And so you get 8x minus 16. Yes, very good. And so that's the force in the x direction. What's the force in the y direction? Well, 0, because there's no y in there. So if you take a derivative, so basically it's like taking a derivative of a constant. You're treating x like it's a constant. Oh, and remember the negative. Oh, so this is all wrong. Okay. So negative d partial with respect to y of this thing equals 0. So there's no force in the y direction. There's this force in the x direction. And the relationship between those so notice that this has to satisfy work is equal to negative change in potential energy, where the work, has to satisfy that integral relationship. So this is just f dx in this case. And so it all comes out being the same thing. Okay, what about, watch this. Ready to have your mind blown? No? Anybody who's not, go out in the hall. Okay? Ready? Okay. Gravitational potential energy is mgh. I'm going to call. So if our y-axis is up, I'm going to call this mgy, right? So what's the force field applied by gravity? Negative mg. Pretty great.
That's pretty snazzy.
What? You don't follow?
Put it like a force.
Oh no, I follow. Because if it was the derivative of x, y would just be a value. So it reacts as a constant, right? Okay. Sure. I'll believe you. Just this one style.
So that potential energy function, even though the potential energy is a scalar, it contains all that vector information inside it in a way, and you can get it out in this way. And what about the spring? So let's say, well, spring potential energy is 1/2 k x squared. That's if the object is moving in the x direction. That's the definition. That's how you get that is the relationship. That is the relationship between the force field and the potential energy function. Yeah, that's a good idea. Bless you. But you know what that negative? You know what that negative does? Remember that the potential energy, if the only forces acting on something are a potential energy field, and the thing starts at rest, the thing always goes to a lower potential energy. That's what that negative enforces. The force pushes you to a lower potential energy. No. Oh. I see. Okay. So the spring. So this is the potential energy function for the spring. So what's the force field of the spring if the thing is moving in the x direction? Well, this is negative partial of 1/2 kx squared, and so that's equal to negative kx. Fy is equal to 0, and that's the force field of a spring. Yeah. What? Can you memorize that? Sure. It's not necessary to memorize it. It's just a cool relationship, like that potential energy function, even though it's a scalar, inside of it is all the information you need to make the vector force field. And this leads to a whole field of differential equations called potential theory that someday you might find interesting. Okay, so let's do 18. Let's do 18 because it's the same thing, right? Okay, so the only forces acting on this object are two potential energy fields. The first one is this, and the second one is this. And basically, like, we want to figure out the total force field. What forces are acting on this thing? Well, the total potential energy function is U1 plus U2. So that's 5x plus 2y squared. And so the x component of the total force is negative partial with respect to x of the quantity 5x plus 2y squared. And the y component is negative partial with respect to y of 5x plus 2y squared. So just take a second and do that calculation, all right? And then, all right, so the x component of the force is negative 5. Who got that? Good job. Good job. You didn't do it. Bad job. Okay, and the y component of the force is 4y negative. Okay, so that says that the x, no matter where the object moves, the x component of the force is constant. It's just 5 newtons or whatever units you're using. And the y component of the force gets bigger as you get, bigger magnitude as you get larger y value. This relationship maybe says something too about, remember that potential energy functions only exist for conservative forces. Who remembers what the definition of a conservative force is?
Oh, wait, it depends on position.
Yes, if you know the position, you know the force. I did first, and then, yeah. Well, okay, so, but look at what this says, like those forces that we derive from the potential energy function are always going to be functions of position. And so you can't have this relationship between any function and a force field unless the force depends on position. You know what I mean? Okay, that's enough of that. Number 14. So number 14 says a mass hangs from the ceiling by a cable. A mass, capital M. Oh, we did something like this in class.
But in the notes, it cuts off. It's like, now go do this on the board.
Oh.
And it's not in the like
Okay.
notes.
Well,
Yeah.
I'll see if I got it.
Okay. So it's a mass M. It's shot by a bullet. The bullet has mass little m. It swings up to position. Okay, so it swings up to a position where its center of mass has risen a height h. That's the change in the heights. Bless you. What's the speed of the bullet? So we're trying to figure out the speed v. Well, there's two parts. We're going to break this up into two separate problems. The first problem is the collision part. And what are we going to use for the collision? It is inelastic, conservation of linear momentum. Yep, exactly. You'll never say anything as loud as Henry in your whole life. What? I don't know. Inelastic conservation of linear momentum. Yeah. And then after that, the two things, together swing up to that maximum height. And that's conservation of energy. Mechanical energy. I'm going to work it backwards, just because it goes a little faster that way. So first I'm going to do the swing. And if you think about a free body diagram of the mass with the bullet lodged in, the forces are a centripetal force from the cable, does no work, and then a weight force that's conservative. Yeah. So this is big M plus little m times g. Conservative forces is the weight. Non-conservative forces are the cable tension, but it does no work. So we know we can use conservation of mechanical energy. So instant 1 and instant 2. So what physical instants do these represent? Yeah. That's right. So like maybe say the instant that bullet is lodged in and is stuck there permanently, that's instant 1, and instant 2 is when it gets to the highest point. And At instant 1, the gravitational potential, we have to choose 0 height. Let's choose, if we choose our h equals 0 to be at that hanging height of the mass, then the h we solve for is what we want. So let's do that. Okay, so what's gravitational potential energy at instant 1?
It is m plus
G times height, which is 0.
So 0.
Yep.
And then 1/2, but we can cancel the x out of the mass, right?
It'll cancel out in the end, but let's just keep it all in for now. Because, you know, if you do have excuse me, work done by non-conservative forces, then it doesn't cancel out. So we'll just leave it in. So 1/2 times the quantity. You have big M plus little m. That's not the right V yet. Okay. So yeah, let's call that, I'll call this V intermediate. I don't know. Make up some name for it. Squared.
And then we figure out using what the inelastic crashing. Yeah.
Okay, so what's the potential energy at instant 2? Yep, times 9.81. Let's leave that as G. So GH, yep. And then what's the kinetic energy at instant 2? Yep, it's at the highest point, so this is 0. And so conservation of mechanical energy says 1/2 times the quantity big M plus little m times VI squared is equal to the quantity big M plus little m GH. And yeah, we can cancel out the masses. And so VI is equal to square root of 2GH. And now we'll do the collision. And the collision for an inelastic conservation of linear momentum, we know that the mass of the bullet times its speed before the collision, well, really times its velocity component, but we're assuming it's moving in the positive x direction, plus the linear momentum of the block before the collision is equal to the combined mass times the velocity of the combined thing after the collision. And what's that? That's our V intermediate that we just solved for. So that's square root of 2GH. And so the speed of the bullet before the collision is big M plus little m quantity over little m times the square root of 2GH. Nice.
Can we do all of that on the new homework? With like the carnival and stuff.
What?
Okay, the carousel, I just parameterized things and then did it that
I
way.
just I drew
Probably
two
it's
question
the
marks.
physics.
And like,
No. What? So
Rigid body kinematics.
can I see those?
Yeah.
Oh, well, all that is just, it's a reminder. It's going back to circular motion, all of it. Yeah, let's do a couple of those.
Let's do the carousel one where they move up.
What? Yeah. Okay.
We'll get it.
Okay, so number 4. It's called rigid body kinematics, right? But Rigid body kinematics is really just circular motion. That's what it doesn't tell you. That's what the deep state doesn't want you to know. It's equals circular motion. Yep. Okay, so there's a carousel. It has a radius of 6 meters.
Okay. He's doing his best.
Thank you.
It's a horse. It's a carousel.
No, if this game doesn't work out, I would ride the
Carousel design. It's a good idea. Oh, horses' knees don't go that way, I don't think. I think I'm just going to leave that leg on. I don't really know what horses' knees do. Oh, I think they have hips that work like our knees, and then... Okay. The kid's riding this carousel. No, it's a kid. It's a carousel. Use your knowledge of carousels to imagine what the different components of this drawing are. What? Yeah. You think those are real horses? Okay, so this carousel is rotating this way at 0.8 radians per second. The radius is 6 meters. And the seat being the horse, moves up and down. Yeah. So the horse moves up and down. Yeah. So the horse moves up and down with the function y equals 0.5 times the sine of t. What's the rate of speed, rate of acceleration, and all that stuff?
Wait, is the answer like 4.8 7.5?
Well, let's go through. So the position, velocity, acceleration, you can do all of these with relative motion. So the velocity of the child relative to the ground, that's what we're talking about, is equal to the velocity of the child relative to the carousel. Those both start with C's. Let's say, okay, kid. Kid relative to the carousel plus the velocity of the carousel relative to the ground
I think you should spruce up every problem. Not just like every time.
It's too late for that.
Buying 2 cards.
We only have like 2 weeks left.
So next one is about
Yeah. We better do a lecture on Friday. Yeah, it's cumulative. Okay, so yeah. Okay, so what goes in the terms of the relative motion equation? Well, we have that function, so let's just, I did it as velocity. Let's do it as position because that's what we have the function for. It's still the same relative motion equation. And so the position of the kid relative to the carousel is 0.5 sine t. That's like if our coordinate system does this. And what's the position of that spot on the carousel, the floor of the carousel under the horse? What's its position relative to the ground? Well, this would be like 6 times, I guess we have x and z. So this would be like 6 times the cosine of, yeah, so as I'm thinking about this, Yeah, sorry about this. Let's go back to velocities. This will make more sense. So this is position of the carousel. Yeah, sorry. So go back to, so yeah, it's the same exact thing. It's just with velocities. Just so you can make sense out of this in your notes later. Okay, so we know that the position of the kid relative to the carousel is 0.5 sine t. And so you can take the derivative of that, and you get that the velocity of the kid relative to the carousel is 0.5 cosine t.
And then we know that the the biggest cosine can get is 0.5.
Well, so now let's think about the circular motion part, because carousel, that spot on the carousel is in circular motion as the horse goes up and down. Yeah, the angular velocity. So this is 0.8 radians per second. The radius is 6 meters. If we're thinking of the horse being at this point in the circular motion, direction's the velocity. To the right, yep. So, and what's the magnitude? Well, let's do all the directions first. So this is the velocity vector. Is it speeding up or slowing down? No, so there's no tangential acceleration. There is centripetal because there always is. The magnitude of that velocity, how do we figure that out? Yep, perfect. This is equal to 4.8. And so that velocity vector is 4.80. Yeah, this is the velocity of the carousel relative to the ground. So we'll go back to the relative motion at the end. And then the acceleration is equal to the centripetal acceleration. It's in the positive y direction. No. We have to be careful with the coordinate system I drew. So this, I guess, is in the way I have it drawn here, it would be like in the negative z direction. Yeah, that's a pain. Nope. Yeah. Yep. Yep. What? And so now the centripetal acceleration is in the negative z direction. You guys have done this before, right? With 3D coordinates. Haven't you sometime or other? Okay, yeah. Yeah. That's okay, so the centripetal acceleration is in the negative z. It has a magnitude that's equal to v squared over r. So this is 0, 0. Yeah, we'll take a break in a second. Negative v squared over r. So that's 4.8 over 6. V squared, yeah. Okay, so 0, 0 is 4.8 squared over 6. Oh, I know what that's going to be. Divided by 6 is 3.9. Negative 3.84. All right, well, we have the velocity of the kid relative to the carousel. We can also get the acceleration of the kid relative to the carousel. That's equal to 0, negative 0.5. There's another 0 in all these now. Sine t. But anyways, now it's just relative motion. So the velocity of the kid relative to the ground is equal to 4.8, and then in the y direction, 0.5 cosine t, 0. And the acceleration of the kid relative to the ground is, relative motion says, negative 0.5 sine t in the y direction, negative 3.84 in the z direction. And so now you're just looking for the maximum values of those or minimum. Yeah, that one gets a little confusing with the directions, but I mean, I think it seemed more confusing because I went into the problem not going in that direction, and then I had to go back and change stuff. But the basic ideas are not that complicated. We have one motion moving on top of another motion. So we're going to use relative motion for those. And then it's just circular motion to figure out the velocity and acceleration of that point on the carousel relative to the ground. And then you add the two functions up. Yeah, x, y, and z. Yeah, so x and z, the way I drew it, are in the plane of the carousel. And the object's moving up and down in the y direction. Any other questions about that one? Okay. Were there any other ones on this that were hard? That you found hard? That's it? Okay. Let's take a 10-minute break, come back at 5 minutes to 9, and then we'll get to new stuff. Okay, so remember, last time we started rigid body kinetics. And the main equation in rigid body, well, what's the main equation of motion in particle kinetics? That's right. No. So F net is equal to mass times the acceleration of the center of mass. And so we're heading towards the main equation in this that says add up all the moments about your axis. That's equal to the mass moment of inertia about the axis times the angular acceleration. So remember, I stressed the thing with all the analogies, including, so instead of talking about forces with rigid body with rotational motion, we're talking about moments. Instead of talking about mass with angular motion, we're talking about the mass moment of inertia. That's the figure skating thing. Pulling your arms in decreases your mass moment of inertia. And then angular acceleration. So, you know, this one is like F net. This one is like mass. This one is like the acceleration of the center of mass. So before we do this, we have to carefully define these two things. We've already talked about angular acceleration, but we haven't talked carefully about mass moment of inertia or the moment about a point. So the mass moment of inertia about a point is the first one I'm going to talk about. And remember, people normally just call it the moment of inertia, but all this stuff is important. And the definition, there's an integral definition. We talked about this last time, I think. You won't ever have to use this. Oh yeah, I know we did. But this integral definition of the mass moment of inertia about a point is the integral over the entire mass of rho squared dm. So you break it up into these little pieces of mass. Rho is how far that piece of mass is from the point A. And then you add them all up in a Riemann sum, and you get the total thing. I did do one derivation. What was it for? A rectangle? What? Circle? I did a derivation last time, right, of the mass moment of inertia. Yep. Yeah. I think I did, but it doesn't, you're not going to ever have to do these derivations, but if you want to see sort of how it works, I think somebody asked a question about, like, how do you do an integral over mass or whatever, and I sort of did a derivation, but really you're just going to use these formulas. These formulas come from the integration. What? Yeah. I talked about that, yeah, and then I think I did a... this is new notes. Where it says back to rigid body kinetics. I'm going to write this down. Strumpf. Just something to think about while we wait. Okay. So here are here's the mass moment of inertia formula for a few, I guess, for three important shapes. And all of these are going to be with the point of rotation at their center of mass. So about the center of mass. The first one is a slender rod where we're assuming that it doesn't have any thickness. Well, that's sort of, it seems like that would be a big deal to assume that it has zero thickness. Like that's what we're assuming, but it turns out that's a good approximation for a lot of just reasonably slender things. And the reason is that rho squared. Well, I'll show you when we get this second formula. But the formula for this, where A is at the center of mass, which is just the middle. So it has a length L. And the mass moment of inertia about its center of mass is equal to 1/12 ml squared. And where do you think that 12th comes from? Whenever you see a 12th or a 6th or a what? It's probably going to come from integrating polynomials in some way. You know what I mean? Because you get a 2 when you go from the linear to the squared, and then you get a 3, another 3 when you know what I mean? And so you can sort of see, roughly speaking, how this comes from that integral definition. I mean, you can see that that's where it's coming from. Then the second important shape is a rectangle rotated about its center of mass, which is the middle. Yep, let's call this W and this L. And the mass moment of inertia about its center of mass is 1/12 times the mass times the quantity L squared plus width squared. Yeah, so one reduces to the other one as W goes to 0. And the fact that W is squared in the rectangle formula is why that assuming that infinitely slender rod is a reasonable approximation actually in a lot of cases. Because imagine that you have a rectangle that has a thickness of 1/10 of a meter, you know. When you square that 1/10 of a meter, it 100th, you know. And so if you have something that's like 1 meter long and 0.1 meter wide, that's not even, you know, that's still pretty wide. But assuming that that's infinitely slender only gets your answer off by 1%, you know. So that's why that slender thing is useful. And then the last thing we'll do is a circle rotated about its center of mass. And the parameter is radius. And the mass moment of inertia of a circle about its center of mass is 1/2 times m times r squared. Okay, so yes. Oh yeah, good question. Well, you can get the units from the formula. It's kilogram meters squared. That would be the SI units. It's always going to have units of mass times distance squared, mass times length squared. The SI units are a kilogram meters squared. Okay, so today only. I'll be right back. Okay, let me turn this off. Well, these shapes are all we're going to need, so that's great if you're doing all your rotations about the center of mass of these shapes. That's not always going to be the case. So now we have the important question. But what if we're doing rotations other than the center of mass? Because all of those formulas were for rotations about the center of mass of those shapes. Well, in this case, there's a really useful, you can think of it as like a correction term. It's based on the parallel axis theorem. And the parallel axis theorem, the parallel and parallel axis says that you have to be rotating, you know, this only applies if you're talking about rotations that are about parallel axes. That's always going to be the case in 2D, though, because the axis is always going to be like into, out of the page that we're rotating around. But the parallel axis theorem says the mass moment of inertia about some axis A is equal to the mass moment of inertia about the center of mass plus md squared. Yep, where d is distance from the center of mass to the point A. Well, a moment is just a mathematical thing. So a mass moment just, so if you have, so if you have the integral of x times, let's say dq, q is, dq. Let's just think of this as any old variable, okay? That could represent mass, length, area, whatever you want. This is called the first moment of, like the first q moment. This is called the second q moment, x squared dq. And so what we're doing is we're taking the second mass moment, because our q is mass. And so it's a mathematical thing. The way to think of it in physics is it's just telling us how hard it is to get that thing rotating. Some things are easy to get rotating and some things are hard. And that's a measure of how easy or hard it is. What, Henry? I sub whatever is the mass moment of inertia, and I sub COM is the mass moment of inertia about the center of mass. And so the parallel axis theorem says if you're taking the mass moment of inertia about some just general point A, you can get it from that formula for the mass moment of inertia about the center of mass if you add this correction term. So let me do an example. So let's say we have a rectangle with a length of 2 meters and a width of 1 meter and a mass of 5 kilograms. And let's say that A is here. What's the mass moment of inertia about A? Well, the way we're going to do that is we're going to calculate the mass moment of inertia about the center of mass, and then we're going to add that correction term. So the mass moment of inertia about A is equal to the mass moment of inertia about the center of mass plus md squared. The mass moment of inertia about the center of mass is 1/12 times 5 times the quantity 2 squared plus 1 squared. Now the correction term, the mass is 5. Distance squared from the, this is the center of mass. So what's distance squared from the center of mass to A? Well, we're going to go, if you make a right triangle out of this, yeah, so we can just use the Pythagorean theorem. So it's going to be 1 squared plus 0.5 squared. Yep. What? The distance would be the square root, but then we're squaring it, so you don't have to do that. Yeah. So this is G squared. And then we just put all this together.
There's one half L squared plus L squared. Where did you get the +5?
This is the parallel axis theorem because we're not taking the mass moment of inertia about the center of mass. Bless you. We're taking it about another point. And so we have to add this correction term that's 5 times the quantity, 5 times distance squared. And so can someone calculate this? .25 kilogram.
Wait, so that was just in total.
Oh.
It's 8.3 repeating.
8.3 repeating kilogram meters squared. Okay, so if you're taking the mass moment of inertia of something about its center of mass, and then you take the mass moment of inertia of the same object about a different point, which one of those is bigger?
Bigger, the further away.
The center of mass, the mass moment of inertia about the center of mass is the smallest it can be for any shape. The easiest to get something rotating that it can possibly be is if you're trying to rotate it about its center of mass. Because remember, right, and that the definition of mass moment of inertia is how far you're spreading the mass away from your axis. So it makes sense that the center of mass is where stuff is closest to in like an overall sense. Okay. Any questions about that? So that's really all there is to mass moment of inertia. If you have a big value for mass moment of inertia, it's hard to get something rotating. If you have a small value, it's easy to get it rotating. We need to define one more thing before we can use this rotational version of Newton's second law. What's the other thing we have to define? The moment, or the torque. Yeah, the M sub A. So now this is the moment of force about a point. And people just call it a moment, but to define it, you need to know what the force is that's creating it, and you need to know the point that it's rotating around. And also, physics people a lot of times call this, say this is synonymous with torque. So maybe you've heard the word torque. What? Yeah. Well, yeah. Engineers tend to use the word torque as being a very specific application of moments. So, if you want to be an engineer, call it a moment. If you want to be a physicist, you can call it a torque too. You don't have to decide now. And to define moment, we have to give one mathematical definition. And that is cross product. So we've already seen one way to multiply two vectors together. That's the dot product. And when you take two vectors and calculate the dot product between them, the output is a scalar. It's a number, right? The cross product, you multiply two vectors together and you get a vector out. So this sometimes people call the vector product because the output is a vector. And so if you have two vectors A, B, C, and you cross it with D, E, F, the vector that comes out has an X component that's equal to BF minus CE. I know this seems unnecessarily complicated, but a Y component that's equal to negative quantity, yeah, AF minus CD. That was great. Do it again. What's the Z component? AE minus BD. Yeah, so yeah, whichever one you're doing, the X component, cross out the X components here, and then you go B times F minus C times E. That's the cross. Why? It seems pretty random, but I'll try to explain why. That's a really good question. That I don't have an answer. And so, in every case, and the only one that you have to be careful of is the Y component as this negative. But you're always crossing out the component that you're on and then going this minus this.
Well, so you know how to do it, but what is it?
Well, remember with dot product, I gave you another definition that had to do with the magnitudes multiplied together times the cosine of the angle between them. Let me tell you that one too. Okay, so this is, you can think of that as one definition. The second definition, you can think of, so
Why is it negative?
just because, yeah. Yeah, I mean, I think that's sort of just a memory device, really. Product does this incredible number of important and cool things, and how they came up with the fact that this is how you calculate the cross product, that doesn't, I don't know that I've ever known that, but I do know that you will see over and over again that the cross product is a super useful thing. So the second definition is put these two vectors tail to tail. Then the vector u crossed with the vector v is equal to the magnitude of u times the magnitude of v. If we multiplied it by the cosine of the angle between them, we would have the dot product. This is the sine of the angle between them. And now this is a vector, so it also has to have a direction. And it's in the direction according to the right-hand rule. So start with your fingers at the first vector, rotate to the second vector v, and your thumb is pointing in the direction of the answer. Okay. So if you have say that's your vector u, that's your vector v. Start with your fingers in the direction of u and rotate them to line up with v, and your thumb points in the direction of the answer. This isn't going to be really an important thing. Here, let me draw it. It's like, so the right-hand rule always relates a rotation to a vector that's out of the plane of that rotation. Okay, so oh no, that's the left hand. Thank you. Oh, don't do what I did. But I could have used the flip function on my computer. I should have. I didn't think of it, and I was just so embarrassed that I had done the left hand. Okay, so the right-hand rule always relates a rotation. I did it by accident. We were talking about the same thing. Okay. So, like, this would be where U is going this way, V is going this way, something like that. So, which way do you have to rotate? Start at U. Think of it maybe this way. Start with U, rotate it to make it line up with V. Have your fingers go in that direction of rotation, and your thumb is the answer.
And then if you had put your thumb upside down.
Yeah, so if we were doing V dot U, you'd have to take V, rotate it that way, and so your thumb would be down.
Because you try to rotate it to the shortest angle.
Oh, you're right about that. It has to be the shortest angle, right? Yes. And that product, yeah, so let me write a couple important things about the cross product. So a couple of things to notice. You just run. That's why I didn't bring it up until you had a lot invested in this class already. So first of all, do you remember with the dot product, if you had a vector u dotted with a vector v, that was equal to v dot u. The order didn't matter. This time the order does matter. So u cross v is equal to negative v cross u this time. It's going to end up mattering in a lot of ways. Theta, really, I guess if you think about it this way, theta stays the same, but the right-hand rule makes the direction switch. Yep. Yep. Yeah. Okay, so to rotate U to make it line up with V, you rotate it in a horizontal plane in this picture, right? And so
it's the line.
your thumb is perpendicular to that horizontal plane. It's up if you're going from U to V, it's down if you're going from V to U. But if these vectors, if one of these was up like this, then it would be a different plane that you rotate. Yeah. And really it only matters, all this stuff we're talking about only matters in 3D. The problems we're going to do are 2D, so this isn't even going to come up for us really. Yeah. Well, yeah, in 2D, it's always a z component, so you can sort of think of it as a scalar. The second thing that's important is if U and V are parallel, then U cross V equals V cross U equals the zero vector. And the right-hand rule, the cross product, you can think of as being the definition of, well, that's why they call it a right-handed coordinate system. Like every coordinate system that you're ever going to use for the next, there are times when people use funky coordinate systems in physics. But all the coordinate systems that you've used up to this point are called right-handed coordinate systems, and they have the following relationships. In a right-handed coordinate system, you've seen like I and J and K things before, right? I know I used that just briefly at the beginning. Anyways, the x-axis, the I-axis, crossed with the J-axis, the Y-axis, is the Z-axis. The Y-axis crossed with the, oh, let me do it in a different order. This is what people use to talk about the unit vectors, to talk about those axes as vectors. Oh, I thought that was going to tell us, I thought Siri was about to tell us what the deal was with I and J and K. Okay, and then the x-axis crossed with the z-axis is the negative y. Let me finish doing this and then I will. And the y-axis crossed with the z-axis is equal to the x-axis. Those three things define a right-handed coordinate system. If you don't have those relationships for now, for the next couple of years, in any class you take, if you have a coordinate system that doesn't meet those, then everything's going to go haywire with your math. And you can use that component definition of the cross product to see that too. Okay, where did you want me to go to, Henry? Or you see?
Yeah, just like that.
Okay. Okay, that's all. So on Wednesday we'll finish talking about the moment, and then we'll do kinetics problems.